Got that. We're good. Okay, we are recording this class for Ellie.
What,
You've got
Sean?
everybody on?
What's that? Not now. He was. Okay. Yep, I think we're all here then.
Excellent. Okay. Let's see here. Did we do I think we did cover the entire chapter.
We did. Yeah, it's just these last three problems that we've been having trouble on. I think I have number 6 figured out, but I'd like to run that by you to make sure I'm doing it right. But 7 and 8, yeah, I can't figure out either. So
Okay.
yeah,
Let's
so number
take a
6, that's the wheelbarrow problem.
Yeah, and the wheelbarrow problem, like I said, is never going to give you the right answer because I can't
Yeah.
figure out the code on it. But
Yeah, and I know you said that, but I just want to make sure I'm doing it right. So when I check their work, it's right. So can I just tell you how I did it once you pull that up and you tell me if it's right or not?
Sure.
Number 6. Okay, so they're giving us, let's see. Yeah, they're giving us the angle above the horizontal.
This one right here.
Yeah. And then they also give us the angle above the horizontal for the handle.
So that's this one, and they also give this one here.
Right.
Right. So we'll call this theta handle. We'll call this theta of the load.
Okay. So essentially I use that the force in is going to equal the force out times the length out divided by the length in.
Yeah, and that is true as long as you're using the length this way.
Right.
Right. And so you end up having to use the sine or the cosine in this case, actually.
Yeah. So yeah, so the length, so that would be your length in, correct?
So the amount of force that you're putting in is this one.
Right.
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 And so this one would be your length in, and that would be equal to the length of the handle times the theta handle times cosine theta handle. So you take length of the handle.
Right.
Times cosine theta handle. And the reason that we're not using the sine in this case is because the angle between the force and the handle is actually this one. And then you would use the sine because this would be opposite it. But they've given you this one, so we go ahead and use the cosine.
Right.
So that's the torque that you put on the handle, and that one is causing a clockwise motion. We could put a negative sign on there. Okay.
Yep. Okay. And so then your length of your out, which is from your
this one here.
Yeah. So that's going to be times cosine of that angle.
Yeah, and this one's causing a counterclockwise. So this would be the distance to the load times the cosine of the load. And these are your two torques that have to add up to equal 0, right?
Mm-hmm.
And you could do this from the whole idea of the mechanical advantage thing.
Mm-hmm. Yeah, and I think that's what I used.
And if you're going to do that, if you're going to do that, that's fine. You just have to be very careful. It's the same equation. The mechanical advantage equation comes from the sum of the torques equals 0. There's no real difference between it. I prefer to do this method because it makes more sense to me rather than memorizing a formula.
Okay.
But this one, I'm adding two torques together. They have to equal 0. And the things that I know are the length of the handle. I know the angle of this. I know this angle. Each of these has a force attached to it too. We have to multiply a force on each of these. So this is the force. We'll call this one F, and we'll call this one L for load. So this one's times force. This one's times L right here. So then we have, we'll call this little L for length of the handle. So now I know the I know the length of the handle, I know the angles, I know the distance to the load, and I know the amount of the load. So I know everything here except for this force. So when I solve this equation for this force here, I'm going to get, and I'm going to do this all in my head, I'm going to subtract this on both sides and then divide by everything in front of the F. So I'm going to get F equals the load force times the distance to the load times the cosine of theta divided by the length of the handle times the cosine of theta with the handle, like that. And that's what you end up with.
Yeah, and that's what I had, so.
Yeah.
Yeah. Okay,
And,
so I think we're okay on that one. Do you guys have other questions
okay, yeah, let's do some more questions.
on those? On this, is that wheelbarrow one okay?
Yeah.
Okay.
For the length of the load, is it the hypotenuse from the center of gravity to the center of the wheel, or is it just the one?
It goes from, so
perpendicular?
that the distance to the load goes from here to here. And they actually, let's see, the center of mass is 0.9 from the wheel. And that's, I should say center of wheel there, I can change that. But that is the number that they give you right there.
Okay.
And like I said, I'm not sure why the code on that is so messed up. I need to go back and look at it again. I've changed it like 3 times and I haven't been able to get it quite right for some reason. But I will change it again. I'll fix it again.
So yeah, so I think we can move on to 7 then.
All right. The cat and the sardines. This is a good one. I'm pretty sure the code on this one is working properly, but it's possible it's not, I suppose. So with the cat here, what we need to do is, when every kind of problem like this, first of all, we need to define where our 0 point is. So we're going to measure essentially our coordinate system. So we're going to measure all of our distances from that point. And the best way to choose a 0 point is to choose a point where there's going to either be forces that you don't want to mess with, or rotational points. So if this cat walks out onto this thing, where is this thing going to rotate about?
Where it's touching the dock.
Right at the edge of the dock though, right? Not just any old point along the dock, right here, right? That's where it's going to rotate. So that's where I want to measure my points. And the reason is because once this board tips up a little bit, the only force that the dock is exerting on it is at that point, and we don't know anything about that force, really. It's going to be messy. We don't want to mess with that. So we're going to put our point there so that we get no torques from that force, and we don't have to mess with it at all. But then the cat is going to be somewhere out here at that point, right? It's not going to be where he is. He's going to be out here trying to get to the sardines. And we don't know that distance either. So we're going to make that our unknown distance. We're going to call it X. Now, all the other stuff we know. We just have to be very careful about the way that we label it. So we have the entire length of the board. It's 5.6 meters. We know that 1.9 meters of it is sticking out here. I need a different color. That's not going to work. 1.9 meters of my board is sticking out right here, right? And then we also know that's also the distance to the can, right? And we know also that on a board like this, that the force from gravity acts on the middle of the board as long as it's, the weight of the board is evenly distributed. So right here in the middle, we have the weight of the board that acts downward. And that point is a certain distance from here to here we need to calculate. And that's going to be half of 5.6. This is half of 5.6. Subtract off the 1.9 will give us that distance between the edge between our rotation point and the middle of the board. So half of 5.6 is 2.7, right? 2.8 minus the 1.9, that gives us 0.9. So right here we have a distance of 0.9 between the edge of the pier and the weight, where the weight acts on the board. And that's something to always remember, is that there is this idea that for an object, the gravity acts on the center of mass. The gravity acts on that place where the average, you could think of the average distance point for the mass or something like that. We call it the center of mass, right? And what the other forces that we have involved, so that's one force. The other forces we have involved are the weight of the can. And I always say weight of cat, but then that's also C, so I call it weight of the kitty. W sub K. This one's weight of the board. Right? So we have three forces: the weight of the board, the weight of the kitty, the weight of the can. We know the distances to each of them. This is the distance to the can, 1.9 meters. The kitty, the distance to the kitty is the unknown distance, x, and the weight of the board is at 0.9 meters from this point, right? And we need to say that the sum of all the torques has to add up to 0. So we'll start off, left to right. The weight of the can torque is going to be the torque of the can. And that one is trying to make this whole thing rotate counterclockwise. So we'll call that a positive torque. And then we have the weight of the kitty, which is going to be also a positive torque. So this is torque can plus torque kitty, both positive torques. And then the weight of the board is trying to cause a clockwise. So that one's going to be negative torque of the board. Let's fill in these torques. Torque is distance times force. In this case, all of the angles are 90 degrees, so we don't have to worry about the signs. So distance times force for the torque of the can is going to be the 1.9 meters times the force, which is the weight of the can, mass of the can, whatever that is, 0.3 kilograms times 9.8. And there's going to be a 9.8 in each of these, so we can actually leave it out. If we leave it out on each of them, we'll be fine, because we'll divide it out eventually. Then we put the torque from the kitty cat. That one's going to be a distance of x meters, which we don't know. The weight of the cat, we have the mass of our cat is 7 kilograms. So that's a 7 kilogram cat times g, which we're going to scratch out. And then we're going to subtract off the torque from the board. The distance to the board to the edge of the thing here is the 0.9 meters. That one ends up being 0.9 times the weight of the board, which is the mass of the board times gravity. Mass of the board is 5 kilograms. And then by times gravity, which we'll scratch out. So this ends up being our equation we solve for x. And that's actually D, I guess, in this problem. And everything else we know. Did that make sense to everybody?
Yeah, is this the mechanical advantage one, or is it just the equilibrium?
This is just the sum of the torques equals 0. The mechanical advantage for this one will not necessarily work, because the mechanical advantage assumes you only have 2 forces. This has 3 forces, so you're not going to be able to use it very effectively unless you combine 2 of the forces, which is just too much work to mess with. So mechanical advantage is really good for machines like a pry bar, a pair of pliers, a wheelbarrow, a shovel, tools and things like that, because there's usually just one input, one output. And whatever. It's mostly just to show you. I think the real reason for mechanical advantage is to give you a number for how useful a machine is, and just to kind of give you an idea why we use machines. Why do we use a lever instead of just picking something up? Well, because you can pick up something that's 10 times bigger if you have a mechanical advantage of 10 or something like that, right? It's mostly just illustrative rather than a real problem-solving tool.
Okay, I think we're all good with that, right, guys? Okay. So we can move on to 8.
Number 8, okay. And this one here is actually very similar to the cat one, but it's also a bit different because we still have, so it's always good again to start off by labeling things and sketching things out. Last time I started off by choosing where I was going to put my rotation point because it was pretty obvious where it was going to rotate. On this one, I don't think it's as obvious to most people where to put that point to make it most advantageous. So what I'm going to do first is I'm going to just label things and then we'll figure that out later. So I'm going to say, okay, we've got some forces acting here. We have the weight of the board here, acts at the middle of the board. And we've got distances. So 5.8 meters divided by 2 is 2.9 meters on each side. So this is 2.9 on this side. 2.9 meters on this side to that point there. Then we have our window washer, and he has some weight. We'll call this the weight of the man. He's got some weight as well, so that's some force that's acting downward here. And then it says here that the rope on the opposite side of the board that he's standing on is damaged. So this one over here is damaged, and it can only support 300 newtons before it breaks. And what we're trying to do is figure out how close he can get to it before it breaks. So right before it breaks, how much will the force be on, how much tension will be in this rope right before it breaks? That'll be the 310 newtons, right? Right at 310 newtons is where it's going to break. So we don't want it to get bigger than that. So we're going to say that there's a tension upward here of 310 newtons where at the point where we're trying to solve this problem. On this side, there's also a tension upward. We're not sure what the tension will be there. We'll just call it T. That's fine. They actually want to know what that is eventually, so we'll need to know that. The thing that they want to know is the distance that he can get to the damaged rope. How close can he get to this rope here? So we're trying to calculate this distance from here all the way over to here. Now this distance here is what we're trying to measure. And so immediately, some people might say, okay, well, we want to know that distance, so we should measure all of our distances from here. And that'd be great. The problem with that is that we don't know what this tension is here. So if we measure all of our distances from here, from this side, then we're going to have to calculate a torque from this tension on this side. We're going to have to know something. We're either going to have to know what this is, or we're going to have to simultaneously calculate it while we're doing the problem. What I'm going to do is I'm going to actually measure all my distances from this side of the board. This is actually where it's going to rotate if this one breaks, right? So that actually makes sense as far as rotation goes. You could measure them all from here and solve the problem. It'll cause a little bit more difficulty. But if we measure all of our distances from here, including this unknown distance, then that will be better. So what is this unknown distance if we measure it from this side? Well, from this side, we have to take the entire length of the board, which is 5.6, and subtract off the distance we're trying to solve for. And that will be the length of this little bit here from here to here, whatever that is. This is 5.6 minus d. So that's going to be the distance that we use with the weight of the man to calculate our torque. The distance for the force for the weight of the board is going to be the half the board, 2.9 meters. And the distance for the 310 newtons of tension on the far side is going to be the entire length of the board. And now we're ready to go. So there are two equations. The sum of the torques has to equal 0. These are vectors. And the sum of the forces has to equal 0. From the sum of the torques have to equal 0, we have the torque from, let's go ahead and put in all the torques here. We have the torque from the tension on the left side. And that one is not going to cause any particular rotation about this point. So this ends up going to 0. It ends up going to 0 also because it's a 0 distance away from the point that we're measuring from. But we also have the torque from the weight of the man. And that one is trying to cause a clockwise torque. So that one's going to be negative torque of the man. And then we have the weight of the board, also a clockwise torque. So that's going to be negative torque of the board. And then this tension force over here is causing a counterclockwise torque. So it's positive torque from the 310. We'll just call it torque 310, whatever. So when we calculate these torques, again, we're in a nice situation because there's all these 90-degree angles between our distance, which is all along the board, and our forces, which are 90 degrees to the board. So we don't have to worry about the signs of the angles or anything. And we get the torque of the man, so it's minus the torque of the man, which is the distance to where the man is, which is 5.6 minus d. Times the weight of the man, which is the mass of the man, times gravity. Now this time we have to include gravity because this last torque doesn't have gravity included in it. From the cat one, everything was weight, and so everything was multiplied by gravity. In this one, we can't eliminate that. We just have to use the mass of the man, which in our case is 64 kilograms, times gravity, 9.8. And then we have to put in minus torque from the board, which is the weight of the board, so that's 2.9 meters, times the weight of the board, which is 14 kilograms, times G. So there's those two torques there, and then the final torque is from this rope pulling up on it, and that's a positive torque. And that's 310 newtons is the force, and the distance is 5.8 meters. And of course, that has to equal 0. And the only thing we don't know in this equation is D right there. So you'll solve that one for D. Now, how do you get this part? This part is just from this equation here. The sum of the forces has to equal 0. And the forces that we have is we have tension is an upward force, it's positive. We have the weight of the man, which is negative, down. We have the weight of the board, which is negative, that's down. And we have the tension from the 310 newtons, which is up. These two you know, this one you don't. They have to add to 0, solve for t, and you're done. And that's part B. So how did that help? Did that help?
It did help me. Yep.
Good.
I don't know. I was missing parts.
That's okay. It's totally understandable. When we get into torques, it feels so strange and it feels so unlike everything we've done so far. Like we're dealing with forces and vectors and things, but it's very different. And the reason is because we just made these up. Physicists just made up the idea of torque. It's not something we have a lot of intuition for. The only way that we have intuition for it is when we go to open a door, but we do that so often we don't think about it, you know. For everything else, it's very, very few people have a great feeling for torque. People who work on cars generally do, because they're in cars. You have to give bolts a certain amount of torque. It's required to give them just this amount of torque, no more, no less. And they understand that because they have torque wrenches, and the higher torque wrenches have longer handles. Well, that means a bigger R. So for the same amount of force that you push on the wrench, with a bigger R, you get a bigger torque. And so people who work on cars generally have a better feel for torque, just because they get a lot of practical experience with it. But in general, torque is very difficult to understand because it's something that we just make up to explain how forces affect rotation. And so it's very, very non-intuitive. Very, very normal to be a little confused by torque. In fact, it's very normal to be very confused by torque. So no big deal. We call it a pseudo vector for that reason, the fake vector, made up vectors. We do this more than once in physics. We do all kinds of things like this to make, to try to make the connection between what we have experience with and what's actually going on, right? So it's not uncommon for physicists to do this.
Okay.
Anybody else have any other questions or anything else you'd like to learn from this homework, from this chapter?
I put that stuff in for the cat one and it wasn't working.
Your cat one is not working?
Mm-mm.
Okay, hold on a second. And the cat one is number, which one is that? Here we go.
7.
You're very, very close, except for one, there's one digit that's incorrect. Your tenths digit is incorrect. So that just makes me think that you maybe added something incorrectly somewhere. I'm assuming that you just added something incorrectly. You have 3.542. The answer is 3.742. So it's probably just some adding error. I wouldn't worry too much about it. You want to just punch in the right number, you can do that. That kind of error is almost always just some arithmetic somewhere. We don't really care about arithmetic errors as long as they don't persist constantly.
For number 2, that equation one,
Yep.
do I put in like theta for the angle or just like x?
Number 2.
Yeah. For
What
that
is the
sum.
torque applied to a range? The point where the force applied are the torque. Okay, so in this one, let's see here. In this one, there is if you draw this out, you got your wrench here, right? That's nice, nice wrench, huh? So the distance right here is your R. And your force is applied here, and your 90 degrees is here, right? And so they've given you R for the distance. So you just want to say that it's F times R times the sine of 90. Now 90 degrees, the sine of 90 has a value. So you want to go ahead and simplify that to 1. So this just ends up being F dot R.
Yeah, and then you would move stuff over because mine wants the force.
Oh yeah, if you wanted to calculate the force, then you would divide by R and you would get torque divided by R.
Yeah,
And
and it's
to
saying
do
it's
that,
wrong.
go ahead and write it as tau divided by R, like that, I think. Or they might, you might use the, use these little things in here where you can actually choose some expressions. Let's see, do they give you a tau? Doesn't look like it. So you actually have to write in tau divided by R. Like that.
Okay.
That should work. Didn't like that.
Counted it right on mine.
Well, that's good. It didn't work for me, but. Oh, sorry, it's not tau, it's F. You wanted, yours one, because mine doesn't want that, right? Mine is still F times R. I'd have to reattempt a different version. Any other questions?
I don't have any.
Good to go. Well, we're just about out of time. If you do have any other questions, feel free to email me. I will be available over the break. I don't remember, did we ever get started on chapter 10?
No, we did not. We decided we were going to start that after break.
So we'll start chapter 10 a week from today. We should have time to get through all of chapter 10 and maybe even do another chapter after that. We'll see. We'll have two
Yeah,
full
we don't have school Monday or Tuesday of next week.
Okay. So
So
we'll meet next Wednesday. Let me make sure I put
Yeah.
that on my calendar.
Yeah, so Wednesday will be when we meet again.
Let's see.
Wednesday, the 2nd, December 2nd.
Got it. So I have canceled the Monday meeting. We'll meet Wednesday. Okay, so we'll probably just finish up chapter 10 and not worry much about the rest of those chapters for now. Well, let's see. What time? When are you out for Christmas break?
The 17th is our last day.
So the same as us. Okay. What we'll do is we'll finish up chapter 10 and then we'll do the chapter 6 through 10 exam. And we could do it one of two ways. We could either start again in January and do fluid dynamics, temperature, and stuff like that, waves, or we could just start. We could start with semester 2 material if you want to go on to electricity. It's just kind of up to what you guys want to do. The final chapters in this class are not necessarily required all the time for this class because they're just we kind of just touch on them. We don't get very deep into them. So we'll think about that. You can think about that over the break, whether or not you'd rather touch on the thermodynamics, it's fluids, thermo, and wave motion essentially is what we cover in the last 6 chapters. And it's just super quick. Just a cursory kind of introduction to those things. But then the next semester starts up with electricity, and we go pretty deep into electricity and on to other topics. Personally, I like the electricity better than I like the temperature and thermo and waves and stuff like that. Waves is kind of fun, but I definitely prefer electricity to temperature and fluid mechanics. Just so you have something to think about over the break. Enjoy your Thanksgiving.
Okay.
Like I said, if you need anything over Thanksgiving break, I will be available. But we will get back to this on the Wednesday after the break.
Okay, thanks.
No problem. See you later.
Bye-bye.
So yeah.